Yes, I'd like to start, like everybody, by thanking Patrick, Etienne, and Valentin for inviting me here to present recent work. So, in contrast with Steve, a very inspiring talk, I've chosen to present you the results of a single behavioral modeling study, which is unpublished at the moment, which, although distinct from metacognition per se, overlaps, I think, broadly with the issue of the internal covert signals upon which metacognitive processes operate, and processes and signals which, at the behavioral level, generate overt variability in choice behavior. And in this study that I've conducted with Etienne and Jan Drugovic now in Geneva, we've considered variability not as a nuisance term or as a scaling parameter in the models we've used, but we've tried instead to study the origin and structure of the variability of the internal signals during evidence accumulation and belief formation. And actually, the question we asked is, we believe, the very general question in experimental sciences, where, as experimentalists, we observe variations around an observed phenomenon. And the question, when you observe variations over a phenomenon that you're looking at, is whether these variations only reflect actually an incomplete or inaccurate understanding of the phenomenon. So they're only pseudo-random variations that are due to the fact that you're not understanding the phenomenon correctly, or whether they reflect the intrinsic probabilistic nature of the phenomenon you're looking at. Okay, so you can think of this problem in particle physics, for instance. And the goal of experimental sciences in general is to partition the variability that you observe between these two forms of variability. So if we now frame this issue in cognitive psychology, it's a general issue because human choices are typically very variable and often vary far beyond the variability in the external world. And so the question is, what fraction of the behavioral variability that you observe can be ultimately explained as a deterministic output of mental processes? And on the other hand, which fraction reflects the finite precision of the underlying neural computations and representations that are involved in this process? And in the study that I'm going to focus on today, we've studied human choice variability resulting from mental inference during perceptual categorization. And so that's the collaborators. So just to explain you the paradigm, which is a very simple paradigm inspired from the weather prediction task, we've presented subjects with a probabilistic categorization task, where subjects are going to see on each chart a series of visual samples that we framed as cards that can be drawn from one of two decks. So this is one card here, and the card is only defined by the orientation of this orientated grating pattern around the circle. And the two decks can be what we framed as a pink deck or a blue deck. And here you can see the principal orientations of the two decks. So subjects are going to see a series of n samples drawn from one of the two possible decks. And at the end of the stream, they're going to make a choice as to whether they believe the stream to be drawn from the pink or the blue deck, right? And they're going to get feedbacks afterward. So there is, in this task, in contrast to earlier formulations of the weather prediction task, here we use the constant probabilistic mapping between the cards and the decks, and I'm going to show you this afterwards. And so what subjects should be doing in this task is, after seeing each card, computing the log likelihood ratio of observing this card given that it's generated from the pink or the blue deck, and integrate, using simple Bayesian inference, these log likelihood ratios across the cards, and at the end of the stream, decide upon this sum posterior belief whether it's more likely to be generated from the pink or the blue deck. So importantly in this task, all the uncertainty that was faced, that our subjects were facing, was regarding the uncertainty of the deck. Okay? Each card, the subjects could easily categorize the card as being pink or blue. The problem was whether the sequence as a whole was generated from the pink or the blue deck. And just to show you what probability distributions we used for the two decks, so here you have the orientation that the cards can take, and on the y-axis you have the PDF for the blue deck and the pink deck. And as you can see, the task was made difficult, not by making the sensory stimuli more noisy or more difficult, hardly perceptible, but just by reducing the concentrations of these circular Gaussian distributions, right? So as you can see, one card on its own had only low predictive power as to which deck it was generated from. So here I'm showing you this card, but I can also show you that card. Okay? And in this task, we manipulated the complexity of the inference process in two different ways. The first way was by varying the number of cards that we presented to the subjects before the decision. And the second way was by varying the number of decks that the subject had to choose from. And we used only two conditions here, the simplest canonical two-deck situation and a more difficult three-deck condition. So there is a very qualitative difference between these two scenarios, because here, as in classical formulations of the drift diffusion model, you can reduce the evidence accumulation process as a single particle drifting from one bound to the other. As instead here, people really have to maintain a multidimensional belief about what is generating the sequence that they're looking at. And so the problem is really qualitatively more difficult in this case. And when we looked at behavior from human subjects in this task, when you split the trials by the number of cards that subjects had seen before the decision, we found what you could say hallmarks of evidence accumulation, like the fraction of correct choices regarding the generative category of the stream was parametrically increasing when we increased the number of cards that we were presenting the subject. And on the dashed line, you can see the performance of the noise-free bias optimal observer. And it was the same in the three-deck condition. But as you can see, and as is often the case in decision-making tasks, the performance of the human subjects were substantially lower than the bias ideal observer. And the very important question that we wanted to address in this task was, where did this variability originated from in this task? And looking at the literature to date, we found three main candidate sources of variability that could be responsible for the choice variability we observed in this task. The first source of variability, which is still often pinpointed as a main source of variability in perceptual decision-making, is variability at the sensory stage, which means in this task, imperfections in orientation processing when looking at each of these cards. A second possibility would be that the variability originates from variability at the inference stage. It would mean that actually this theoretical Bayesian update process would not be done perfectly, but would be done in an approximate fashion. And the last source of variability could be a source of variability at the selection stage, when subjects at the end of the stream are deciding whether they want to respond pink or blue, and they only have imperfect information as to whether they should be responding pink or blue. So yes, so just to show you, of course, so variability at the sensory stage would be due to that. When looking at this card, people would perceive actually on different trials these different orientations. Variability at the inference stage would mean that this sequential Bayesian update process would only work approximately. And variability at the selection stage would correspond to a softmax decision rule, that people would not always pick the deck that has more evidence, but would do so in a posterior sampling fashion. And the good thing in this particular task is that these three sources of variability have overlapping but distinct statistical signatures that we could compare and use Bayesian model selection to decide which was decisive in explaining choice variability. So to do that, what we've looked at across the different sequence length was to look at the variability in choice behavior that was intrinsic, meaning that we've removed the variability that was caused by variability in the cards that we were presenting the subject. That this is only variability that was not explainable by the cards that we've shown the subjects. And as you can see, the variability that we observed in the resulting choices was increasing linearly with the number of cards that we've presented the subjects with, as if the variability in choice behavior was really increasing every time the subject is adding a new card to his posterior belief. And so this could be explained by variability at the sensory stage. This could also be explained by variability at each inference step. but it could not be explained by posterior sampling, as the variability of choice behavior should be constant across different sequence lengths. So at this point, we can already rule out in these tasks that subjects are drawn by selection-based variability, or variability in action selection. The pattern was strictly similar in the 3-deck condition. And we could also now rule out sensory variability as a primary source of choice behavior, because if you look now across the two conditions, the 2-deck and 3-deck condition, at the estimated sensory variability, if you assume that variability in choice behavior originates from sensory variability, you can notice two very unexplainable facts. The first thing is that the quantitative orientation discrimination threshold that you would need to fit subjects' data with sensory noise would be of the order of 20 degrees, which would mean that your subjects are probably half blind, and it was not the case in this task. And the second, even more disturbing fact is the fact that this orientation discrimination threshold, although the cards were perfectly identical in the two conditions, was significantly larger in the 3-deck condition, in the task that was more difficult in terms of inference. So this fact makes also this sensory account of choice variability incompatible or inconsistent. So if you apply proper Bayesian model selection with the 3 sources, when you contrast the 3 possible sources of choice variability, you find that in both 2 and 3-deck conditions, the inference source of choice variability is capturing the choice behavior a lot better than the 2 other sources. And even if you allow in the model for the 3 sources to explain choice variability at once, you find that around 90% of the overall variability is explained by variability in the processing of the evidence, not variability in the sensory input, or not variability in the action selection process. So at this point, we could already find something that is not often assumed in decision-making models. For instance, if you think of simple learning models, when people model, for instance, probabilistic reversal learning tasks, they use reinforcement learning models where actually the variability of this model is 0. All the variability in this task is often put at the action selection stage, but they assume that this TD or this updating rule is done perfectly. And here in this task, we find that actually, if you make stimuli seeable and not noisy, you find that all the variability is at the core of the decision-making process, not at the peripheries, so not at the sensory level, not at the action selection level. And we think that it has been often overlooked in decision-making studies, and so it's an important first fact. Now we went on to our second question, whether the variability that we observe was not only due to approximations in the Bayesian update process, but also for the subjects to have used another generative model that is not the Bayesian model. So actually the variability that we could have looked at could be either deterministic and could be due to the fact that we have not modeled the way people integrate evidence in this task, or the noise could be really stochastic per se. So we used what we call the bias variance partitioning of the choice variability, where the bias term in this task would come from deterministic distortions of the bias optimal inference that we've used up to now, and the variance term would come from really the finite computational precision of the mental inference process. And to do so, what we looked at is not the fraction of correct choices that people often look at in this task, but also the fraction of consistent choices when you compare decisions to repetitions of the exact same sequence of cards. And by looking at this fraction of consistent choices, we could split the choice variability that originated from mental inference into these 2 terms, and we could quantify how much of the variance in choice behavior could be explained by these 2 terms. And so just to show you the idea behind this view, imagine that you're looking at 2 repetitions of the exact same sequence. And here we're looking at something that we cannot look at behaviorally, which is the internal noisy log posterior that subjects have at the end of these 2 repetitions of the same sequence. You could imagine 3 scenarios. A first scenario where, apart from having the same mean, the noise in these 2 repetitions, these 2 noisy log posteriors, are completely decorrelated. So the noise correlations would be 0. And you can imagine different scenarios where, at the end of this evidence accumulation process, if you look at the Bayesian log posterior, they would be perfectly correlated across trials. In this scenario, it would mean that all the variability you're looking at in behavior is a variance noise. It means that the noise is uncorrelated and it's due to the precision of the computations. But here, if you find noise that looks like this, it probably means that the variable you're looking at here is not the variable that subjects use to generate behavior. And so the variability would be mainly due to deterministic distortions that you have not captured with your Bayesian log posterior. And the good thing is that these three scenarios make different predictions regarding the overt fraction of consistent choices that you can measure behaviorally, so that the fraction of consistent choices will grow linearly and parametrically, not linearly, but parametrically from here to there. And to make things a bit more complicated, we also not replicated twice the exact same sequence, but we also perturbed the sequences that we replicated. So for instance, we used a temporal perturbation whereby when we presented the sequence in this order on the first instance, we presented it in a shuffled order in the second instance. The good thing is that in terms of Bayesian computation, it is completely the same. So a Bayesian model is completely oblivious and blind to this perturbation. And we use also a feature-based that we call spatial perturbation, where we, on the second instance of the sequence, presented each card flipped relative to the category center of the sequence. And again, in terms of Bayesian computation, this is completely blind, but it could be actually doing something to subjects' behavior. So when you look at the fraction of consistent choices for these different scenarios, where you repeat exactly twice the same sequence, or when you perturb selectively the temporal domain, the feature domain, or both, you find two main effects. And the first important thing is that if you look at just perfect repetitions of the same sequence, you find that the fraction of consistent choices in human subjects exceeds the one you would get from a Bayesian observer that would be corrupted by pure variance noise. So it means that part of the variability in human choice behavior is actually due to subjects not using Bayesian inference or optimal Bayesian inference to do the task. And by looking at the contrast between these perfect repetition condition and these perturbation conditions, you can find, for instance, here, that part of these distortions are found in a temporal domain, because you find that when you compare perturbed sequences in the temporal domain, the fraction of consistent choices drops significantly. And we found a similar pattern in a 3-deck condition. It was a bit more pronounced. So now the question that is begged after this slide is, what are the forms of these deterministic distortions? So if you look in the spatial domain, so now what we did was we not only assumed that subjects were using the actual theoretical information provided by each card, but we really fitted the function that subjects use to convert the orientation of each card into information for one of the 2 decks in this condition, or for one of the 3 decks in this 3-deck condition. And we compared the human data, which are the dots and the lines behind it, to the dashed lines, which were the Bayesian optimal function. Here it was just 2 sinusoid functions. As you can see in the 2-deck conditions, subjects approximated quite well this optimal function. And subjects in the 3-deck conditions feature different kinds of biases that were making them go further away from the Bayesian optimal computations. And now in the temporal domain, we found something that was completely replicated across the 2 conditions, which were a recency effect or a leak effect, as if subjects were becoming blinder and blinder to evidence that was found earlier in the stream and further away from the decision. So this is what we found. But then the most critical quantitative question is then, at the end of the line, how much of the choice variability that you observe is ultimately unexplainable by variability in external variables in the environment and is only due to variability in neural processing. And if you do that in the 2-deck condition, you find that the variability can be split with 70% of the overall variability due only to this unstructured variance variability, and for 30% to deterministic biases. Okay? And among these deterministic biases, the ones I've showed you already make up, in this condition, for a very large part of it, around 80%. The good thing is that this split was actually relatively preserved in the 3-deck condition. So the 70-30 split between the deterministic and the unstructured portion of variability was kept. And the also important thing is that in this condition, which was more difficult for the subject, the typical biases that we could find in the literature, the deterministic biases, could only explain 50% of the overall deterministic variability in choice behavior. Meaning that if you don't use this approach and if you assume that aside from your model, all the variability you have is non-deterministic, you're going to overestimate it by a very large amount, which is this gray portion. Okay? And this unstructured variability is then causing a very large amount of information loss in the information that was provided to the subject, even in the simplest two-deck condition. So here you can see that on average, this unstructured variability was causing almost 30% of information loss in the information provided by each card. So actually, I'm already close to my conclusion. So we found that in this perceptual categorization task, in contrast to what had been even reported very recently in the literature, the inference process was causing a very large amount of variability in choice behavior. In typical tasks, it is often conflated with sensory or selection-based variability. And in the field, people have often overlooked this source of variability. It can here constitute more than 90% of the total choice variability. And the second important fact is that most of this variability was caused by unstructured noise, and so by the finite precision of the computations that were done during mental inference. And this method, we believe, provides somehow a behavioral estimate of the precision of these computations. That actually, the best way to get is behaviorally by looking at choice. If we had looked at neural data, we wouldn't have been able to find this behavioral estimate because it's really an effective estimate of the precision that you can only get by looking at the output of inference, which is the behavior that subjects generate. And it's also important, the method that we developed, because it affords to distinguish a misspecification of the model that you have to explain your subject's data from the truly stochastic fluctuations in choice behavior that are irreducible. And one of the take-home message is that it sets, we believe, a surprisingly low bound on the accuracy and the consistency of human decisions. And closer to the topic of this seminar, if this noise is truly representational, then metacognition should be blind to it. So it should take it as fluctuations in the sensory evidence, in the evidence, and it could not use error monitoring process to capture this. At least we are now running tasks where we ask specifically confidence to see how much we can really back that claim up. And yes, so I'd like to thank you all for your attention.